Hello and welcome to Book Bites, a book club podcast for developers. We're continuing our summer of an imposter syndrome by talking about The Imposter's Handbook by Rob Connery, which is a CS primer for self-taught programmers. So today we're going to go over chapters 8 and 9, Advanced Algorithms and Compilation. I'm Adam Garrett Harris.
I'm Safia Abdallah.
I'm Jen Luker.
And I'm Jason Staten.
All right, so what about advanced algorithms? I think you kind of mentioned here he's kind of using the term advanced loosely. It's kind of just like algorithms part 2. But I don't know, some of these are kind of complicated.
Yeah, I think their argument was that you are more likely to use some algorithms than others. Like no one's really going to make you do a bubble sort, but you're going to end up using some of these others more often.
Yeah, I like that description where you had mentioned that these are more likely the things that you're going to get paid to do versus going and writing your own bubble sort is probably not going to keep your employer happy if that's what you're doing.
Yeah, so it's like these are solving real problems and they're not necessarily going to be built into the language or the library you're using.
So let's talk about it.
Dynamic programming.
Hey, there you go.
Yeah, so it brings up dynamic programming at the start. Like, what was your takeaway? This is kind of open to whoever about what dynamic programming is.
Nothing. Absolutely nothing.
Yeah, I'd never heard of it before.
I was going to say, it was one of those things that brought horrific flashbacks to my undergraduate computer science courses. Because I did learn about dynamic programming in an algorithms course. And I think the big thing was that the way that I learned it in my course was like very theoretical. And in hindsight, now that I've been in the industry for a while, I think the like mathematical basis of dynamic programming is a lot less important to grasp than the approach that it lays out for problem solving. Obviously, when you're in college, you're like given problem sets, people expect you to have a proof and a solution for something. And I was getting really caught up in that. And one of the things that this chapter kind of helped remind me of is that it's not really about the details, but about the general approach that dynamic programming kind of embodies. So yeah, I liked it.
What is the general approach?
Yeah, so I would say if I could break it out into a simple phrase, dynamic programming is about taking a problem and breaking it into a smaller, more manageable problem, and then building on top of that. So for example, let's say that you're asked to like sort through a list of 10 things. Well, first you would start off by solving the problem of sorting a list of just 9 things, because that's less complicated to solve than sorting 10 things. And you can kind of break it down further and further, like we talked about in, I think it was the last chapter actually, where we were talking about merge sort and how you kind of break it down into the smallest possible piece, and then you remember what those individual smaller solutions were and build up to the bigger problem. I hope I'm explaining this well. So in my mind, that's what dynamic programming is really about, is when you're given a huge task, find a task that's smaller, solve that, and see if you can use the solution to that to solve your bigger problem.
Sounds like the divide and conquer approach that we talked about last time.
Yeah, a little bit. I think one of the key elements to dynamic programming, well, I'm not totally certain of this, is that recursion is a big part of it, which I think depending on how you implement divide and conquer, you might be using recursion. But I think the idea with dynamic programming is that like the function you use to solve for n is the same one you would use to solve for n minus 1 and for n minus 2. And you can kind of nest those calls and store the solution, like memoize it, and then build it back up. Wow, this is so weird when you have to like explain the way you perceive things out using words and stuff. Communication's hard, huh?
Yeah, and I like how he says that memoization is like a fancy word for caching.
Yeah.
And I always think it's funny. Like when you say memoize, it sounds like you have a speech impediment and you're trying to say memorize.
Yeah, it's kind
I've
of
never
a funny
thought of
word.
that.
I'm just going to memoize this.
Yeah, I wonder. Yeah, it is a funny word.
I'm so glad I'm not the only one that picked up on that.
So yeah, I guess that's my take on it, is just there's like way more formal steps about it. Like if I am sorting a list of n items, how might I go about sorting a list of n plus 1 items? Like what would I need to do to make that jump to like solve for the next case? And that's where the recursion comes in. Sorry, I'm getting into the details again. It's so hard to break away from that because like I think the details are definitely important to grasp of dynamic programming, but I think the more relevant thing and the thing that I think is more applicable in the day-to-day life of a software engineer is just if you have a problem, see if you can try and break it up into a smaller problem and then build back up from it.
Yeah, that makes sense.
So breaking something down into a smaller problem and then using the solution to those pieces to create the total solution sounds nothing like a dynamic thing to me, which, you know, it sounds much more like recursion or something. So I loved the story of the origin of the word dynamic or the words dynamic programming. What did you think of that story?
Yeah, I thought you were about to tell it. Why don't you
Okay.
go ahead and tell the story?
Okay, so the story is essentially, without reading it out, is that a man named Richard Bellman was trying to do mathematics research in the 50s, except for the fact that there's this guy named Wilson as the Secretary of Defense. And he, as the book quote says, actually had a pathological fear and hatred of the word research. I'm not using the term lightly, I'm using it precisely. So in order to avoid the anger and frustration of the Rand Corporation and the Secretary of Defense, he came up with dynamic programming is essentially a translation for mathematical research, which kind of turns around and says it means absolutely nothing. And it's been assigned this algorithmic thing because that's kind of what it resulted in, was discovering some of these algorithms that we're going to talk about in a minute. But I just thought that was an awesome story that the definition actually has nothing to do with the name because the name was technically to hide the concept of mathematical research.
Yeah, it's just all political.
Yeah.
It kind of reminds
Politics.
me of a term that we run into a lot now. So there's this scary idea of, think of having a server that's exposed on the internet. That's scary. But if you call
Ooh.
it something fluffy and nice like a cloud, then everybody's on board.
Oh, man.
You know those are still
Yeah.
servers, right?
The cloud is just someone else's computer.
Right?
When
It's just not
you
your
really
own.
just want to get rid of the server, just go serverless.
Exactly.
And then serverless isn't even serverless.
No, it's not.
But yeah, I think
Anyway.
so that kind of, oh my gosh, I'm going to go on a tangent again. Stop.
Let's hear it.
Yay, tangents.
But no, I thought it was just interesting, this conversation that we're having about the words that we use to describe things in our field and where they come from, and how it kind of circles back to the original thesis of this book, that oftentimes one of the most confusing things about the industry is the jargon. And this conversation we just had like a certain level of self-awareness. And, you know, even the story that Jen pointed out, in which Bellman shared the origin of the word dynamic programming, there's like a certain level of awareness that the ways in which we describe things do have like a sense of ambiguity and like lack of precision to them. So yeah, I just thought that was an interesting discussion we just had and kind of interesting historical context to it.
Our ability to explain things poorly started in the 50s. Or, you know, the dawn of time.
Yeah.
Yeah, so the first type of problem it tries to solve is generating a Fibonacci series, which I'm sure we've all done.
Have we all done it?
I don't know. Yeah, that's a good question. Have we?
Yes.
Yeah.
Yeah, and I'm sure you did, Jason, right?
Yep. Yeah, I went and did it inside of Rust, and
Of course.
Yep.
yeah.
Of course you did.
Well, that's my whole goal for this, right? And
Yeah.
I found that Rust is, I mean, not just Rust, but computers are really fast. So
Yeah.
by doing it, I don't have an example of the slow way of doing it with recursion and building up a new stack frame every time. I just kind of skipped straight ahead and made an iterator sort of pattern of it, where it becomes a greedy algorithm, which we can touch on in just a minute. And because of that, it becomes so fast that I had to go and start finding like the 150th Fibonacci in order to start even having Rust benchmarks show something that was not 0 nanoseconds for it to run, and the number size is as big as I can get it inside of an unsigned 128-bit integer. So it's really big. I don't know how many digits it is. I'll have to count that sometime, but it's really big, and I am impressed with computers that they're super fast. So when you all implemented it, like, did you start with like the classic recursion style? Like, is that what you were first exposed to?
I actually started doing it for a Scrum counter thing that someone else immediately wrote in much better than me. But it was just so that we could estimate stories, which meant I only needed to go up to 144. So yes, I kind of did it the slow way and then optimized as I went.
I don't remember the first time I did it, but I did it in an interview, and it was actually on paper instead of a whiteboard, strangely. But I did it. I did it with a for loop. I believe I iterated, and then I did that pretty quickly. And then they said, okay, now do it with recursion. And I remember in the interview really struggling with recursion because I just hadn't quite wrapped my head around it, and I hadn't done it in a long time. And I felt like I totally failed that interview, but actually ended up getting that job. So
nice. Maybe you spoke your mind well enough, or it like gave people the understanding of how you're working through the problem. Because hopefully that's what they were looking for, and not for you to solve Fibonacci as fast as possible.
Yeah, I was definitely speaking out loud and got pretty close, and they were like, okay, yeah, I see where you're going with this. And one of the problems I had with it, I think, was I was trying to output the entire series instead of just the nth number.
I think that gets into the greedy topic, as far as I understand. So the book talks about greedy algorithms, and it describes them as an algorithm that does what's best at the moment. And so if you don't need, say, the entire list of all Fibonacci's, but if you just need the nth Fibonacci, then just calculate that and don't worry about the rest of the list of them. And that can benefit you by, I guess, first space-wise, like you don't have to go and hold all of those numbers somewhere. So for calculating n Fibonacci's, you don't need to consume n numbers of space, but instead you only have to consume a single, so a space complexity of 1, which is much better.
Oh, and I feel like we should explain for the listener who's not familiar, a Fibonacci series is a series of numbers where each number is the sum of the previous two numbers. And one thing I learned from this book is I always thought it started with 0 and 1, but you can start with any two numbers.
You can, but traditionally it starts with 0.
Yeah, 0 and 1.
And 1. What's also interesting is that if you take any two numbers besides 0 and 1 and 1, I think it's actually after you get to 3. It's like 3/5 or 8/5. It's actually divides out into the golden number.
Oh, right. It starts if you divide the number by the previous number, it starts approaching the golden number.
Yeah, and there's a way that you can use that you can generate Fibonacci's like crazy fast, like it up to a certain point. So if you instead of actually going and doing the addition, if you just do like a single multiply against it, you can get it up to a really large number before you start to get inaccurate. I know that was like a Project Euler thing, because you had to calculate some like huge Fibonacci or something, like I think Fibonacci 1000 or something. And so in order to do that, you have to be fast. So I will dig for that, see if I can find something on it, because I remember I was kind of blown away that you could just multiply up to a certain extent.
Yeah, take 55 and multiply by 1.61, and it's essentially 84.
Yeah.
Okay, so I thought this section was pretty interesting, talking about heuristics. And it mentions the traveling salesman problem, and how it's NP hard, and one heuristic to solve it is nearest neighbor. And so that was kind of what I was mentioning when we were talking about heuristics last time, is nearest neighbor is just pick the nearest city, and it's going to be pretty good most of the time.
Yeah.
But that's also an example of a greedy algorithm.
Prior to recording this podcast, I was planning on doing a planned tangent. So this one's not spontaneous.
Nice.
But just to kind of elaborate a little bit more on the greedy algorithm section, and specifically the heuristics portion that Adam just covered.
Thanks,
And
Adam.
basically,
You're welcome.
yes, Adam's just setting me up. He warmed up the stage. Now I gotta get up there and deliver, and hopefully I do with this tidbit. So I was just, researching because this section in the book lists a few greedy algorithms, but I was like, can I go out and pick a few more to share with people so you all have a better sense of what they are? And so I thought a little bit about some of like the different things that I had done at university courses that were solvable using greedy algorithms. And one of the ones that I found that I thought would be a good segue from some of the things covered in this chapter is around job scheduling. And we'll probably touch on this a little bit later, but your CPU on your computer can technically only execute one piece of code at a time. Let's assume that it's like a single core CPU from 1991 or something. So it can only execute one piece of code at a time. And the reality is that you as a programmer might be wanting to run code from different programs at the same time. So maybe you have your browser open, and maybe you have like your text editor open, maybe you've got your Spotify open, and your CPU has to very quickly schedule those processes in such a fashion that you don't notice the fact that it's switching between which code from which process it's running. And one of the ways that it does this uses greedy algorithms. And by the way, the example I'm presenting now is specifically for like scheduling processes on your CPU, but really this could apply to anything that's like, I have a list of things I need to do, like a job, and I know it's going to start at this time and it's going to end at this time. So I know how long it'll take. And I want to figure out what is the sequence in which I should do these jobs. And greedy algorithms come into play here. And essentially, there's a couple of different techniques for doing it. You might do a greedy algorithm where the local optimization that you make is something like you always pick the job that's going to start first. So it's just sorted. In the end, you get all of your jobs sorted by in ascending order by when they started. You might also pick when the job ends. So you pick all of the jobs that will end sooner, earlier in the process. Or you might optimize by greedily choosing always the job that's going to be the shortest to complete. And one of the things about greedy algorithms is that although they are generally optimal, they're not always optimal. So in some cases, you might be in a situation where you're scheduling like 6 different jobs and you can only do 2 of them at the same time, and there's some conflicts involved. So you can't do like job A and job C at the same time. And if you're picking a heuristic in a greedy implementation, like I'm going to do the ones that start earliest first, you might actually end up in a situation where you're not completely allocating your job board as well as you should, or things are taking longer than they need to finish because the dependencies aren't mapped out right. So yeah, that was my little tangent. This like general problem or area, if you're interested in learning more about it, is called interval scheduling. And you can see how it comes, its applications in like scheduling jobs in your CPU, or just kind of like more general software type applications where, you want to build an app where people can schedule something, or like organize a Gantt chart or something like that. So yeah, that was my planned tangent of other information to share. That's it, Finn. End of short notes.
This should be a segment.
Pull me off the stage now.
I've seen a scheduling problem like that before in an interview where they had like you're an actor and you have different movies that you can be in, and each movie pays you a certain amount, but they have a start date and an end date, so you can't be in any movies that are overlapping during filming, and you have to pick which set of movies will get you the most money.
Oh, that's a really good problem. So yeah, if you're listening and you're somebody who's out there doing job interviews or just solving interesting problems, good to know that if you get that kind of problem statement, a greedy algorithm is a good first approach to take.
It's also something that we encounter even in the web development space. It's like a problem that browsers have to solve is when do they go and update the UI versus running our code? And there is I mean, JavaScript's own event loop, which I won't go down that rabbit hole, but there is like some things happen with greater priority than others. So for example, an update to the browser's DOM is something that's going to happen as a micro task rather than a macro task in JavaScript. And so like if that needs to happen, it will get prioritized before something like a user click. So it'll make sure that the browser draws before the click, because in terms of the browser's algorithm, they've found that that is the optimal path for it, or somebody at some point decided that. So yeah, those algorithms are all around us.
That's really cool.
They're all around us.
Yes.
Everywhere.
Just have to open your eyes.
There's greed everywhere.
Okay, so the chapter concludes with 2 different ways to find the shortest path in a graph. There's the Bellman Ford and Dijkstra's algorithm.
Yep.
Who's going to explain those?
I can talk a little bit about them.
Okay.
I went and implemented Bellman Ford inside of Rust, and I did not actually get around to doing Dijkstra's, just time-wise, didn't get to it, but I still want to do a comparison of them. But a basic explanation of the Bellman Ford is that you pick some source node in a graph. So say you have a graph of 7 nodes, and they have edges that connect to each other that are directed. So like A can go to B, but not necessarily back to A. And so yeah, it's a directed graph. It doesn't have to. It can have cycles in it. That's okay.
But it's weighted.
Yes. So the edges are weighted. So kind of think traveling salesman problem or something, where like distances or whatever you want to consider to be a weight is. But yeah.
Peta factor.
Yes. And the objective of it is, given a certain source node, finding out what the shortest path to any other node within that graph. And the way that Bellman Ford goes about doing that is you start at that source node, and then you go and find the links for whatever other nodes that it's attached to, and you say like, this is the length for those things. You go and you memoize those values, or you cache those values in some sort of lookup, and from there you progress on to yet another node. And it doesn't particularly matter the order. The book actually questions whether or not the order matters, and it doesn't. But you progress on to another node, and from there you measure the distances between that as well as back from the original. So like if you start at node A and it's connected to B and B is connected to C, then you go and you take B's current length that exists in your lookup table and add it to B's weight to C. And you wind up going and traversing all of the nodes. I guess it winds up being big O of n squared is really the worst case, or like that's the algorithmic complexity of it. And by doing that, as you traverse the tree, eventually you wind up in a case where you haven't actually updated your memoization table. And at that point, you know that your table is what's known as relaxed, or it's stable. And at that point, you know that you have found all of the shortest paths from a given source node for that graph.
Yeah, I like this idea of relaxation, because you start off and assume the distance is just infinite. And then as soon as you find one, you're like, oh, well, that's better. And anytime you find a shorter path, you start to relax. And it doesn't really sound like relaxing to me. It sounds more like tightening, like you're getting closer and closer to the real answer.
Yeah, I don't know. I don't know why the term is relaxing.
I think it's more like it's settling in.
Oh, yeah.
Yeah, I guess if you're relaxing on like a memory foam bed, eventually the bed stops collapsing underneath of you, right? Like once you've relaxed
Hopefully.
enough. Yeah.
Doubt it.
If not, there's a problem.
Right. Yeah, you got to get yourself a new mattress. So, yeah, that is the Bellman Ford. And I did go and look through his algorithm, and there were a couple of things in there that I think could potentially be improved. So if you are on page 205, where it is actually iterating over the table, one of the things that he actually does in this table is he looks up all of the edges for a given, I guess I've been calling them nodes, so I'll stick with that, but he calls them vertices, I guess, or a vertex. But for a given vertex, he goes and finds all of the edges for that. And that isn't actually necessary, I found, when I was building out the algorithm. Rather, like if you just do it against all edges, it continues to work even without doing that check. So it's kind of an unnecessary traversal of the tree or iteration of the tree. So yeah, I was kind of surprised when looking at that, but you don't actually have to do it node by node. It seems weird, but it actually works out just fine. And in all the examples I looked at between like Wikipedia's example implementation, they actually don't care which one you're iterating from. The fact is that you're traversing over all of the nodes enough that it does just stabilize, or the numbers stay consistent. I was kind of mind blown.
Something that he did say when he wrote these algorithms is that he wanted to write them for clarity and not for efficiency. So he assumed that people would find better ways of doing it, and that you'd find things within this that wouldn't necessarily be required, but that it was easier for him to understand it this way. So he was hoping that by writing it that way, it would be easier for everyone else to understand as well.
I will have to talk to Rob about that and see his thoughts. Following up with Bellman Ford, another graph traversal. It's got the same objective as going and finding the shortest path between a source node and any given other node.
Basically, every other node that is reachable.
Yes.
Yeah.
Yeah. So it finds the shortest path between some starting node and every other node. It gives you a lookup of that out of it. And Dijkstra happens to be a complexity of big O log n. So n being the number of nodes or vertices on that graph, which generally it can go and beat out Bellman Ford. And the way that it does that is by kind of improving its heuristics, or taking a different set of heuristics, by always going and following the lowest weight vertice from the given node that you're on. And then once you have done that, then you know that you have traveled that shortest path. The book describes it pretty well with some pictures to kind of...
Yeah, let me see if I can explain it a little differently. So
yeah,
for each iteration, you visit the vertice that has the smallest value that is unvisited.
Mm-hmm.
Yeah, and so you have to keep track of which ones are visited, and you only visit each one once.
Yep.
And kind of like how it comes up with that is it realizes if you're going between points A and Z, and along the way you visited B, if you found the shortest path between A and Z and includes B, then, wow, I just lost my train of thought.
It basically travels to the shortest node and then travels to every single one of its nodes to say, okay, well, if we start at this beginning and we go to this next node and it allows you to go to this next node, this is how much that next node is going to have. And then it does it for every other path it could possibly start with from that point. And then it goes backtracks once it knows it can't go any further and starts again and goes, okay, so that was the lowest node. Let's go to the higher node and see where it can go and all of the paths in which it can go to. And it allows it to go through every single node once, as opposed to having to visit them all over and over and over again to see if every possible iteration is going to be faster than the previous computed iteration.
Mm-hmm.
Yeah.
I actually think a lot more on the lines of the Dijkstra one than I do from the Bellman Ford thought. So the Dijkstra one ran much better with how I naturally looked at the graph and figured out what the numbers were.
So there are a couple of gotchas with these. One is that Dijkstra's algorithm doesn't work with negative weights, because it, like for instance, if you go from the starting node and the ones that are connected to it, it's going to assume that's just the smallest distance. But if there was a negative weight somewhere, that might actually be a shorter distance. Just given the fact that it only visits once, it doesn't take into account negative weights. So if you have a negative weight, you have to use Bellman Ford. But even with Bellman Ford, if there's a negative cycle, then it's not going to work, because if there's a negative cycle, you can just keep looping that cycle to make it smaller and make the value smaller and smaller and smaller.
Yeah. With the Bellman Ford, if you actually want to find a negative cycle, you can do that as well by looking at that produced value of it. And if the weight of any traversal is less than the weight of any given node, you are in a case where you have a negative cycle.
In another book I read, if a Bellman Ford's given a graph with a negative cycle, it should return something indicating that it's unsolvable.
Mm-hmm. So
Yeah.
there are some cases that is actually a necessary thing. I was trying to find like real world use cases, and the closest I could find is some Quora that was talking about like network lookup type stuff that is a little bit beyond me, or like I didn't quite pick up on all of it. But there are some cases that like Dijkstra needs more information available to it than what Bellman Ford needs, and because of that, it made Bellman Ford a reasonable choice in some scenarios, like network lookup wise. Yeah, I can link to that as well, and maybe somebody can explain it to me in simpler terms. But it was good to find a case that, like, even though it's algorithmically better or like time wise more performant, it may not always be the correct choice.
Yeah, and another thing is if you're working with an unweighted graph, then you can just use a breadth first search, because like simply the least number of traversals will be the quickest. Like,
makes sense.
Yeah.
So we've been using the word heuristics a lot, and I'd heard it before but didn't actually know what it was. I wondered if it was like this whole major concept, and the book essentially said heuristics is a fancy word for rule of thumb.
Yeah, it's like a good enough
information that you make a decision on.
Yeah.
So
it's a heuristic as opposed to an algorithm, which will always give you the best answer.
Yeah.
All right. We have a sponsor for this episode, which is vSchool. So vSchool was established in 2013 and is Utah's highest ranked coding bootcamp. And they have some different options. You can learn full-time, choose to learn full-time or part-time in the evenings, and you'll completely immerse yourself in learning new skills. They take care of everything you need, including free housing if you need it. And the housing's just a few blocks from school, so you can focus on learning. And it's located in beautiful Salt Lake City, Utah, or you can learn from the comfort of your own home with one of vSchool's 100% virtual classrooms. If you're interested, they encourage you to take a campus tour. You can meet the students and faculty and even shadow a class. If you're interested, check out vschool.io. And thanks to vSchool for sponsoring this podcast.
yeah, thanks.
All right. How are we going to talk about compilers?
They're hard. Next chapter.
So I think we can start off with the basic steps it goes through. I think I can kind of wrap my head around the basic steps.
Let's even back up and just talk about like what a compiler is before we even talk about the steps or compiler or what compilation is, because that I guess is the chapter. And a compilation is at its core. I tried to describe this at a company meetup once, and it's a machine or something that takes an input in the form of a type of well-structured code and produces some sort of output given that code, and that is very, very high level, and basically it's to say that it's a function. But to boil it down a little bit more in terms of what we do with computers is it lets you write code, say something like JavaScript, and then it can go and turn that JavaScript into either bytecode that V8 can understand, or some languages like Rust, it will go and compile Rust into assembly language. And so you get to type nice high-level human-friendly type things, and it goes and it takes that human-friendly type stuff and through a series of steps converts it into something the computer can understand and execute.
Yeah. And I would also like to point out the difference between compiling and transpiling, because transpiling is a term that I've heard about recently over the last few years with things like CoffeeScript and TypeScript. And basically, transpiling is a type of compiling. So compiling is going from one language to another, and transpiling is going from one language to another language that has a similar level of abstraction. So TypeScript and JavaScript are on the same level of abstraction. It's not going down to bytecode or something lower.
So we're talking English to Chinese versus British to American.
I don't quite understand that analogy.
Maybe like English to Latin versus, I don't know, like something lower level. Because I guess Chinese, I would consider it to be at the same level of abstraction Like, well, I mean, one.
Well, yeah, but I mean, as far as levels of abstraction, it doesn't really matter per se, the level of abstraction. The difference is that you're taking it from one thing that humans understand and turning it into another thing which computers understand. You could say the same things for languages in that we're taking it from one thing an American would understand versus another thing that Chinese would understand. So, I mean, yes, it does continue to go more and more low level in that it's harder and harder for us to understand. But I think that high level and low level in the translation of things is just a human definition of how far away from human comprehension it is without the help of computers.
Yeah, I think I can't find it right away, but there's a list of different levels of abstraction for computer programming languages.
Yeah, there is. I was trying to choose something that was a little bit easier to say that, the difference between compiling and transpiling, I guess. And you could say the trans portion of transpiling would be like translation. So maybe compiling would be a language humans could understand to a language that birds could understand.
Yeah. I'm not great at analogies.
So, all the way down to, something ants could understand.
I'm still, caught at like what the true terminology, because I mean, you can also go in some ways upward. Like, have you heard of like mscripton, where it will go and take like C code and then compile it into JavaScript code?
Which is the argument that it's just, there's no actual true, the levels of abstraction is still just like a human mental construct. There's levels and there's the reasonings in which we say there's these levels. But I think that when you're talking about it, we're still talking about two different languages. We're just talking about JavaScript versus binary.
Okay, so I actually found a little article mentioning the levels of programming languages, and there's machine languages, which is basically zeros and ones. Then there's assembly languages, and then there's high-level languages.
Right.
And that's pretty much it. Pretty much every language we write in is high-level languages, unless you want to get down in assembly. You probably don't want to get down into zeros and ones.
Right. So I'm just saying maybe it goes from, it's like the Rosetta Stone of, languages for us, that it's essentially breaks it all the way down to like hieroglyphs.
Yeah.
Which is also why I chose. I mean, I guess I should have chosen something closer to like Japanese for kanji, but it's still very similar in that it's just translating from one understandable language to us to an understandable language to someone who isn't us. I mean, if we looked at it long enough, we could figure out binary, but we've also figured out how birds talk to each other too. Doesn't necessarily mean we understand it just by looking at it.
Mm-hmm.
Yeah, a good benchmark that I use in trying to figure out, like, is it compiling and transpiling? And this I learned a while back from somebody. I think just like a random conversation you have with people where somebody says something smart and it stays with you. But a good way of kind of, for me, of figuring it out is at the same level of abstraction. Can you say that the way you represent the data in those two languages is relatively the same? So for example, with like TypeScript and JavaScript, how would you represent a string? Well, in memory, a string is like a sequence of characters. And if you were to kind of differentiate that between compiling, the way that, assembly thinks about strings is way different than the way JavaScript thinks about strings. So for me, it like helps to think about how is the data treated, or how is the data represented at each of those levels, and is it different enough to like warrant being called a compiler? So,
and I guess at the same time we're talking about something similar to the squares and rectangles problem. Like, all squares are rectangles, but not all rectangles are squares.
Yeah.
So all of transpiling is compiling, but not all of compiling is transpiling.
Yeah. Okay, so a compiler takes the code through a series of steps to get to that final form.
Yeah. I think probably one of the most important things that is good to take away from the whole compiler process is just the fact that a compiler actually optimizes your code. So, you write a for loop or you write some sort of code, and you can optimize it as much as you like, but the compiler itself is going to go in and make some low-level optimizations based on its understanding of the machine language that it's compiling down to and its understanding of what it is that you're trying to do.
Yeah, and also you may have some syntactic sugar or something where you can write a map instead of a for loop, but underneath the hood, it's probably still just a for loop.
Yeah, which is the point of compilers. Oh, I want to go on another tangent. No, I can't. It's a history tangent that involves Grace Hopper, who is interested.
She is very related to compilers.
Yes.
Go forth.
So, yeah, Grace Hopper invented the compiler. She's super badass and legendary. Her name comes up a lot when you think about women in computing, but unfortunately, most people don't know the actual, revolutionary thing she did was that she invented the concept of the compiler. Prior to her sitting down and saying that you don't have to write programs in low-level machine code, that's not a good thing to do. Instead, you can write programs in a more natural language and then build translators that take that more natural language and convert it into machine code. And
that is so smart.
Yeah, if you think about it, this is it's such a huge deal because it's why we can build software and why we build websites and why Facebook and Google and all these companies exist.
As opposed to punch cards.
Yeah, how hard would it be to build Google in assembly language or some other low-level language?
Telling it which transistors to manually turn on and off.
Yeah. And so it's really interesting. She actually faced a lot of resistance from people who had a gatekeeping ideology around programming and didn't want it to be easier for people to do because there was a sense of elitism or whatever around it. And I think she hopped between a couple of different companies before she actually landed at wherever it was that she built.
I see what you did there.
What?
Hopped.
What did I say?
Grace Hopper hopped.
Oh. Not intended at all, but I'll take it. But yeah, I think that's really cool. So that underscores a lot of the basis of compilers, which is that you as a person can spend time doing things like high-level problem solving, and then you give that code that you write that has your high-level problem solving to a computer, and it takes care of all the nitpicky optimizations and then making it better and all of that. And yeah, that's a big deal, a huge deal. So thank you, Grace Hopper.
That's super cool.
Yeah.
So, Jason, I want to hear about your experience because I know you took some time to build a compiler in Rust. So what was that like?
Well, that's putting a lot on me. I started some of the progress on it. And a good place to start with a compiler is actually going and reading the code that you're given. And that first step in there is called lexing. And what lexing does is it goes and walks through the code, often character by character, and it goes and tokenizes the things that it finds. So if it's reading through your code, it will look like, let's say we were doing some JavaScript, because why not? If you are lexing and you find the letters FUNCTION, then your lecture will say, oh, I found a function keyword, and I'm going to store that. It's not adding any additional meaning to it. All it's saying is I found a function keyword. There's no processing beyond that. And then it will find an opening parenthesis and a closing parenthesis. A lot of times those are tokens of their own. And if it finds a quote, then it will know to continue walking along until it finds a closing quote for that thing. And then once it finds that, it says, okay, I found a string literal. And that is kind of the lexing process, is it goes and it finds pieces of your code that are distinct. So one way to kind of think about it is say you're looking at your code editor. A lot of times certain things are highlighted in there. I'm actually looking at Rust right now, but there's FN that's highlighted, and then the name of the function is highlighted shortly after that. So those are all kind of different tokens that exist within the code. It doesn't assign a lot of meaning to them other than saying like, this looks like this. This looks like an identifier or a number or a string or something. And then after you've lexed your code, the next step is to go ahead and parse your code with a parser. And a parser goes and it starts at your first token, and it knows to say, all right, well, if I find a function, then what should come after it? Most likely it's either a name of the function, if that function happens to have a name, or it's just like a parenthesis, like an open parenthesis. And so like a parser starts to go and put those tokens together and start assigning meaning to those. And for me, like that's always been something that's gotten combined a little bit more between parsing, and then the chapter also mentions semantic analysis. And I've kind of lumped those in my mind of like, it goes and it takes the tokens and it gives meaning to those things. And oftentimes when you are parsing something, you start to produce what's known as an abstract syntax tree, or AST in some cases. And that is like the hierarchy of how the code is laid out. Code that is inside of a if statement. Like you have an if, and you have a conditional to that, and then you have a block or a body of that if. And within that, there is more code. And underneath each one of those things, there are more and more hierarchies of code until you ultimately get to leaf nodes within there. And once you've gone and built out your abstract syntax tree, then you can progress on to some of what Safia was talking about, where you have optimization. So if you happen to find, say, a mathematical expression, like say your code finds 1 plus 2, your compiler can do an optimization pass to say, hey, I know what 1 plus 2 is, and it will always be 1 plus 2. I'm just going to replace those 3 nodes within the abstract syntax tree with a single 3 instead. It can go and find common patterns and go and optimize those things. It can see like, you're doing a for loop here, but you're doing absolutely nothing inside of it. I don't even need to run the for loop if the for loop has no body on it, most likely, depending on the language that you're working with, obviously, because some for loops actually do have side effects just by looping over them. But that is definitely language dependent, and optimizations are a hard problem to solve because you can wind up giving people issues if they are relying on the optimization potentially not happening. So it is definitely a heuristic based thing. And then after it's done however many optimization passes that it decides to do, then you get into code generation, where you go and take that syntax tree and produce some sort of output with it. And that can be something that either a native code, so producing assembly language that compilers know how to understand, or it is also something that can be an intermediate language, like say you're writing Java or C#. They have an intermediate language that their virtual machines know how to execute. And you can also go and produce, if you are transpiling, which is kind of just a subset of compiling, then you can go and produce whatever output language that will potentially get run by some other compiler later on. But that's kind of the process of writing a compiler at a high level.
So how far did you get, and what type of language were you trying to compile?
So I was following along a guide for, there is a language toolset that's actually brought up in the book called LLVM. And LLVM is short for low-level virtual machine. And it is a way to write. It's kind of like a virtual machine that's super low level in some way, or like a base subset of stuff that you can write to instead of writing directly for a given like CPU architecture. So instead of writing for Intel or AMD or something on that front, if you write to LLVM, then it will be kind of cross-compatible on that front in some cases.
So basically, are you saying you compile from something like Java to LLVM, and then it's like a language that can run on any computer?
Yes. I guess Java would not be the best example, but like a language at the same abstraction or whatever you want to say. But they have a tutorial on their website that I can go and link to called Kaleidoscope, that they have you work out to build this language that kind of looks similar to Python, when you write it. Like you use like def to create a function, and it's super basic. It only has numbers. It doesn't have string literals or anything in it. And they have you work through the process of writing a lexer and parser and producing something that LLVM can take over from there and create workable machine code. And I got through the process of writing a lexer on it. I want to continue onward. Actually, that was something that I attempted to stream over Twitch, and it was pretty ugly. I'll link to it as well, but it was mostly me just struggling with reading some things in with Rust. So it's not that exciting, but I have since found better ways of working with code to lex it. And so I'm going to continue on that process, actually, because I want to make it happen. Like this tutorial makes it seem so straightforward, but it's also written for they have both an OCaml tutorial and a C++. And it's kind of interesting because Rust falls kind of somewhere in between, where it's got a nicer type system than C++, so some of its things are well suited there, but then and more like OCaml-ish. But at the same time, they're using like a parsing library that OCaml has available that Rust does not. So it's like, just use this thing, and I don't have that available.
So at what point in the compilation process does the compiler find errors?
It can find it at really any step within it. So if you're lexing and you're searching for tokens and it comes across something that it doesn't understand, like right there, it can bail out and it can say, you tried to go and put an emoji in here, and this language does not support emojis or something.
Oh, okay.
And then parsing, you definitely are more likely to run into problems where like it's gone and parsed a token, but then you have put something incorrect, like say you threw a semicolon between your if and it's parentheses after it, then it's going to say like found unexpected semicolon at this position. Like that's probably more common where you'll run into it. And I guess optimization, it probably shouldn't be. Like once you've parsed out something successfully, like optimization should be safe pass over stuff. But those are kind of the places that I can think of. I mean, I guess during optimization, you could go and find things to warn about. Like, for example, Rust will go and warn you if you are doing something you probably shouldn't. That can be a time to also produce warnings during your optimization. You're not actually changing code, but you are at least letting the user know, like, watch out.
Yeah.
Shout out to Jason for being very diligent. Like I said, I really admire the way he's always on top of his learning and just like very proactive about it. I definitely need to do way more of that. I think Jason's a great example of that. So thank you, Jason, for putting in that work. And
everyone be more like Jason.
Yeah, everyone be like Jason.
Everyone needs to be more like everybody else on this. Like everybody does a great job. Like, I mean, Safia, like going back to you, like you're digging in at like node internals and stuff like that. And Jen, you're always giving great talks all over the place. And Adam, like you're organizing this show and many other ones. So everybody has amazing things that they're doing.
Hurrah.
Yeah, go us.
Well, the rest of the chapter kind of gets into garbage collection and some things like that I read, but honestly, I don't have much to say about. It's good to know that it exists, and I don't work with garbage collection that much, so I don't have anything to say about it.
Isn't it awesome we don't have to work with garbage collection much? Is pretty much what that portion of the chapter said.
Yes.
I mean, in one way, you kind of do work with it, but it works so well that you don't really have to worry about it that much.
Well,
so.
I don't have to manually clean up my own trash, apparently, so we're good.
Yeah.
If only life worked like that.
I need life to work like that.
I guess it's called get a cleaner, a house cleaner.
If only.
That has been an enlightening thing about learning Rust. I'm not going to get too much into all the topics, but if you are used to working in a garbage collected language, Rust is not one. And so it puts you in a very different mindset about what you're actually doing with things. And simply just thinking about it and not necessarily saying like, you have to write in a language like this because it's super performant and you have all sorts of control, but it is enlightening at the same time.
I learned to program on C++, so I had to handle that back in the day. And therefore, I greatly appreciate the fact that I don't have to do it now.
Okay, so imagine C++, but you don't have to write malloc or free.
C?
You'll do malloc and free in C. But Instead, Rust compiler will actually do those things for you. It's just embedded in the type information. So you still write like...
So when it compiles, it just adds that stuff for you. Oh, I see you did something. We're going to just clean that up for you.
Yes, but it doesn't do garbage collection, but instead, just by the way that you write your code, it gives it the information it needs to know when to allocate and free memory on its own, and lets you do it in a safe way, so you're never going to go and try and read from memory that you just freed or something. So it does a lot of hand-holding for you. So it's still not like at the same raw level of C or C++ where you're juggling
or Objective-C.
pointers. Yeah, unless you want to. Then you can always break out and go wild in Rust if you want to. But I've only had one situation that I've had to do that, and it was more of an optimization than a necessity.
Cool. Well, I don't have anything else for this chapter, unless y'all do.
No, I think we're good.
Any more tangents, Safia?
Not at the moment. I'm all tangent out. Admittedly, I got 4 hours of sleep last night, and I think I'm hitting my wall.
Well, let me close the show out. So thanks so much for listening. You can follow the show on Twitter at BookBitesFM, and you can follow all of us on Twitter as well. And please subscribe in your favorite podcast player and rate the show if you liked it. And you can also find the transcripts online at orbit.fm/bookbites/13. And actually, we've got a review this time, if someone wants to read that.
I can do it. All right, we've got a review from Jake Lingwall, who says, I was confident that I'd subscribe to every developer podcast I needed. It seemed like many angles from tech to community to interviewing, etc. were covered. And then I found Book Bites and realized that the hole was missing in my lineup. I read tech business books all the time, so this podcast was right up my alley, and now it's part of my regular rotation. Looking forward to being part of the Book Bites Club for a long time. Thanks for being a part of the club, Jake, and be sure to share this podcast with your friends and have them be a part of the club too.
Yeah, I think this is a really awesome review. It's cool to know that we're kind of filling in a hole. That's kind of why I started it. And Jake is a friend of the show, so Jason and I know him, worked with him. So thanks.
Thanks, Jake.
Thanks for making us feel good about ourselves.
Yeah, that's good. All right, well, I'll see y'all next time. We'll talk about software patterns and principles.
See ya.
Bye, folks.
Bye.
See ya.